Welcome, everyone. I'm excited to kick off our session today on advanced programming. Today, we'll be diving into Chapter 7, which focuses on Java database programming. Over the next few slides, we'll explore how Java interacts with databases, including key concepts, techniques, and best practices. So let's get started and see what's in store for us. Let's take a closer look at the contents of this presentation. First, we'll start with an overview of JDBC, which is fundamental for understanding how Java interacts with databases. Next, we'll explore JDBC drivers, which are essential for establishing that connection. Then, we'll discuss statements, the tools we use to execute queries. After that, we'll see how to connect to a database effectively. And finally, we'll tie everything together, highlighting how these components work together to enable seamless database operations within Java applications. This overview sets the stage for a deeper dive into each of these topics, helping you see the big picture of how JDBC functions as a bridge between Java and databases. Let's talk about JDBC, which stands for Java Database Connectivity. It's essentially a complete set of interfaces and classes that enable a Java application to access an underlying database. Think of it as a bridge that connects your Java code to the data stored in a database. Now, JDBC is made up of two main parts, the JDBC API and the JDBC driver. The API defines the interfaces and methods that vendors need to implement when creating a JDBC driver. This means that the API provides the blueprint for how Java interacts with databases. The JDBC driver, on the other hand, is the actual implementation of these interfaces, allowing Java to communicate with specific database management systems. It's important to note that a single JDBC driver is typically designed to work with one type of database. So, if you want to connect to different brands of databases, you'll need different drivers for each. Understanding this helps clarify how Java interacts with various databases and highlights the importance of choosing the right driver for your specific database system. This forms a crucial part of our overall theme, seamless database connectivity in Java applications. Let's take a closer look at the JDBC model, continuing from where we left off. In this diagram, we see the Java application at the center, which interacts with various databases through the JDBC API. The API acts as a bridge enabling communication between your Java code and different database systems. Notice how the application doesn't need to worry about the specifics of each database, whether it's Oracle, DB2, or MySQL. Instead, it uses the JDBC API to send queries and receive results uniformly. Now, to facilitate this communication, each database requires a specific driver. You can think of the driver as a translator that understands both Java and the particular database's language. For example, there's an Oracle driver, a DB2 driver, and a MySQL driver. Each one is tailored to handle the nuances of its respective database system. This setup highlights the flexibility and efficiency of JDBC. By having a common API and specific drivers, Java applications can connect to multiple types of databases without needing to change the core code significantly. It's all about creating a seamless, database-independent way of working with data. This is a key concept in understanding how Java applications achieve database connectivity in a versatile and scalable manner. Let's take a closer look at the different types of JDBC drivers and understand their key characteristics. First, we have the bridge driver, also known as the JDBC to ODBC driver. This driver acts as a bridge, connecting Java applications to a Microsoft ODBC data source. It's useful when you need to connect Java to existing ODBC-compliant databases. Next is the native API driver. This type of driver uses the client-side libraries of the database itself. Essentially, it converts JDBC method calls into native calls that the database understands directly. This allows for efficient communication because it leverages the database's native API. Then we have the network protocol driver, sometimes called a middleware driver. In this case, requests from Java applications are sent to an application server. The server then translates these requests into a database-specific protocol. This setup is particularly useful in distributed environments where middleware facilitates communication. Finally, there's the database protocol driver, or what we call the pure Java driver. This driver converts JDBC requests directly into database-specific network protocols right at the client side. This means Java programs can connect directly to the database without needing any additional middleware or native libraries. Understanding these different driver types helps us choose the most suitable one based on our application's architecture and performance needs. Each type plays a vital role in how Java applications interact with databases, which ties back to our overall theme of efficient and flexible database connectivity. Let's talk about the advantages first. One of the key strengths of this approach is that almost any database for which an ODBC driver is installed can be accessed. This means that data retrieval becomes quite flexible and widespread, since you're not limited to specific database types. Essentially, if there's an ODBC driver available, you can connect and work with that database effectively. Now, moving on to the disadvantages. One of the main concerns is performance overhead. Using ODBC can sometimes slow things down because of the extra layer of translation between your application and the database. It's also important to note that the ODBC driver needs to be installed on the client machine. This can add some setup complexity, especially in environments where managing software installations is challenging. Another point to consider is that ODBC isn't suitable for applets. Since applets run in a restricted environment, they typically can't handle the installation of drivers on the client side. So, if you're developing lightweight or web-based applications that need to access databases, ODBC might not be the best fit. Overall, while ODBC offers broad connectivity, you need to weigh these performance and deployment considerations when choosing this approach. Let's talk about the advantages of Type 2 drivers first. One key benefit is that, since there is no need to implement the JDBC ODK bridge, these drivers are considerably faster than Type 1 drivers. This makes them a good choice when performance is a priority. Now, moving on to the disadvantages, one important point is that the vendor client library must be installed on the client machine. That can sometimes be a hassle, especially if it's not already available. Also, not all databases have a client-side library, which can limit the databases you can connect to using this driver. Another thing to consider is that this driver is platform-dependent, meaning it works only on certain operating systems. And finally, while it supports most Java applications, it does not support applets. So, in summary, Type 2 drivers offer speed benefits, but they come with some platform and setup limitations. Now, let's talk about the advantages of Type 3 middleware. One of the key benefits is that the communication between the client and the middleware server is database independent. This means you don't need to have the database vendor's library on the client side, which simplifies deployment. Essentially, the client doesn't have to be changed or reconfigured when switching to a new database, making it very flexible and scalable in diverse environments. However, there are some disadvantages to keep in mind. For instance, you do need to implement database-specific coding within the middle tier. This can add complexity because the middleware must handle various database protocols and features. Another point is that adding a middleware layer can introduce some additional latency, potentially impacting performance. But this is often mitigated by using more sophisticated middleware services that optimize data transfer and processing, ensuring that the overall system remains efficient. So, while Type 3 offers great flexibility, it requires careful planning to manage the added complexity and potential performance considerations. All right, let's talk about Type 4 drivers and their advantages. One of the main benefits is that no translation or middleware layers are used, which directly leads to improved performance. Because these drivers communicate straight with the database, there's less overhead and faster data exchange. Additionally, the Java Virtual Machine, or JVM, handles all aspects of the application-to-database connection. This can actually make debugging easier because everything is managed within the JVM environment, giving you better control and visibility during troubleshooting. Now, on to some of the disadvantages. The key challenge here is that drivers tend to be database dependent. Different database vendors often use very different and usually proprietary network protocols. That means a driver designed for one database might not work with another without some modifications or different drivers. So, while Type 4 drivers can boost performance and simplify connection management, their dependency on specific database protocols can limit flexibility across different database systems. This is an important consideration as we look at choosing the right driver for our applications, especially if we need to support multiple databases. Let's take a look at some popular JDBC drivers that are commonly used to connect Java applications with different types of databases. As you can see in the table, each RDBMS has its own specific driver name and URL format. For example, with MySQL, we use the driver named com, MySQL, JDBC, driver, and the database URL typically follows the format JDBC, MySQL //hostname/database name. For Oracle databases, the driver is called Oracle, JDBC, driver, Oracle driver, and the URL format is JDBC, Oracle, thin@hostname, hostname, port number, database name. This format is slightly different, emphasizing the thin driver. Moving on to DB2, the driver name is com, IBM DB2, JDBC, net, DB2 driver with a URL like JDBC, DB2, hostname, port number /database name. For Microsoft Access, we often use the com, JDBC, JDBC ODBC driver with a URL such as JDBC, ODBC database name. And finally, for JavaDB, which is often used in embedded scenarios, the driver is com, org, Derby, JDBC, Clint driver, and the URL looks like JDBC, Darby, database name. Understanding these drivers and URL formats is essential because they form the foundation for establishing successful database connections in Java. It's important to choose the right driver for your specific database and correctly format your connection URL to ensure seamless integration. This is a key part of working effectively with databases in Java applications. Let's take a closer look at slide 11, which is an overview of JDBC and its key components. First, it's important to note that the JDBC interfaces and classes are part of the JavaSQL package. This package provides the essential tools we need to interact with databases in Java. So, what exactly does JDBC do? Well, it helps us establish a connection with a database, which is the first crucial step. Once we're connected, JDBC allows us to send SQL statements. These are the commands that tell the database what data to retrieve or modify. After executing those statements, JDBC processes the results, turning the raw data into something our application can understand and use effectively. Now, when it comes to actually using JDBC, there are several steps involved. Think of them as a clear sequence to follow. First, we load the JDBC driver, which is like telling Java how to communicate with the specific database we're working with. Next, we define the connection URL, which contains the details needed to locate and connect to the database. Once we've set that up, we establish the connection itself. With the connection in place, we create a statement object. This is our way of preparing to send SQL queries. Then, we execute the query, and JDBC handles the communication with the database behind the scenes. After execution, we process the results. This involves reading the data returned by the database and doing something useful with it. Finally, it's good practice to close the connection, freeing up resources. In summary, these steps, from loading the driver to closing the connection, are the fundamental process flow when working with JDBC. Understanding this flow helps us build efficient and reliable database applications, connecting seamlessly with the overall theme of working with databases in Java. Once we have established a connection to the database, we can start interacting with it directly. The JDBC API provides several key interfaces, such as statement, prepared statement, and callable statement, that are essential for executing SQL commands. These interfaces define the methods you'll use to send queries and updates to the database, as well as to receive data back. It's important to understand that these interfaces also help bridge the gap between Java data types and SQL data types. Because Java and SQL have different ways of representing data, These methods ensure smooth data transfer and conversion. Overall, once connected, these JDBC interfaces are your primary tools for communicating with the database, allowing you to execute commands and handle results efficiently and effectively. This is a fundamental part of working with databases in Java, and understanding these interfaces helps you write more robust and reliable database-driven applications. Now, let's take a closer look at the JDBC statements and understand how to choose the right one for your needs. The first one is the statement interface. This is best suited for general-purpose access to your database. If you're running static SQL statements at runtime, this is the way to go. Keep in mind, though, that the statement interface does not support parameters, so it's best when your SQL queries are fixed and don't require user input. Next, we have the prepared statement interface. This is ideal when you plan to execute the same SQL statement multiple times. It allows you to set input parameters at runtime, which makes your code more efficient and easier to manage, especially with dynamic data. Prepared statements help prevent SQL injection and improve performance when executing repetitive queries. Finally, there's the callable statement interface. This one is used when you want to access stored procedures within your database. Similar to prepared statement, it can accept input parameters at runtime, but its main purpose is to invoke predefined procedures stored directly in the database, enabling more complex operations and business logic to be executed on the server side. Connecting this to our overall theme, selecting the appropriate JDBC statement type is crucial for writing efficient, secure, and maintainable database interactions. Each type serves a specific purpose, so understanding their differences helps us choose the right tool for the task at hand. Now let's talk about creating and closing statement objects. When you're working with a database, you need to create a statement to execute your SQL queries. To do this, you use the create statement method of the connection object, like I've shown in this example. It's pretty straightforward. Once you have your connection, you call create statement and store it in a statement variable. It's just as important to remember that, just like with the connection object, you should close your statement object when you're done with it. Closing resources is crucial to prevent memory leaks and to make sure your application runs smoothly. All you need is to call the close method on your statement object, and that will free up the resources. In the example here, notice how we first initialize our connection, statement, and result set objects to null. Then, inside the try block, we create the statement and execute in SQL insert command. After the try block, in the finally block, we close the statement with statement close. This pattern ensures that resources are properly managed, even if an exception occurs. So the key takeaway is, always create your statement objects using create statement, and don't forget to close them with close once you're finished. Proper resource management helps your application stay efficient and reliable as a whole. Once you've created a statement object, you can use it to execute SQL statements using one of its 3 execute methods. The first one is Boolean execute, which takes a SQL string as a parameter. It returns true if a result set can be retrieved, meaning the query was successful and returned data. Otherwise, it returns false, indicating that no data was returned, such as in an update operation. The second method is execute update. This is used when you expect the SQL statement to affect a certain number of rows, like with insert, update, or delete statements. It returns an integer representing how many rows were affected by the execution, which is useful for confirming the impact of your operation. Finally, there's execute query, which is used specifically when you expect to get a result set back, typically with select statements. It returns a result set object that you can then process to access your data. These methods are key because they give you flexible ways to interact with your database, depending on what kind of operation you're performing. Connecting this to our overall theme, understanding these execute methods helps you write more efficient and effective database code by choosing the right method for each situation. Now let's look at JDBC result sets. When you execute a SQL statement that reads data from a database, the data is returned in what we call a result set. Think of the result set as a container holding all the rows that match your query. These rows are what we refer to as the result set itself. To access this data, you typically use a cursor, which allows you to move through the result set one row at a time, usually from top to bottom. The Java.SQL result set interface is what represents this result set in Java, providing methods to interact with the data. Within a result set, there's a cursor that points to the current row you're working with. This cursor moves as you navigate through the data, enabling you to view or modify the row's contents. The methods available in the result set interface can be grouped into three main categories. First, navigational methods, which help you move the cursor around, like moving to the next row or jumping to a specific position. Second, get methods, which allow you to view the data in the columns of the current row the cursor is pointing to. And third, update methods, which let you change the data in that current row. The really powerful part is that these updates can be written back to the database, keeping your data synchronized. So, understanding how to navigate, view, and update data within a result set is fundamental to effective database interaction in Java. It ties directly into the overall theme of managing and manipulating data seamlessly through JDBC.